Welcome to today's lecture. Today what we will do is we will now come out of this relaxation time approximation and free electron gas and try to understand the physics of electrons in a material, in a condensed system. At the moment we will only consider solids. So, why do you want to abandon the free electron model? It is not that we are abandoning it, but there are so many results that did not come out right using classical gas approximation for electrons along with relaxation time approximation, that one realized that this is not the correct approximation, the correct theory of metals, electrons in metals, and then of course, one has to go beyond. And the first signature that this theory of classical gas is not the right theory came when the specific heat of many metals were measured, and it was found that the estimate from classical theory is hugely large, very large. It is hugely overestimating the specific heat in most cases. And then of course, there are many other issues that came out. For example, the magnetoresistance, for example, magnetoresistance in this theory of when we did the Hall effect, we showed that it should not be the rho of xx, the magnetoresistance as a function of in the longitudinal direction along the direction of the current, the resistance along the direction of current in transverse field should not be field dependent, should have no field dependence in it, whereas the actual measurements show that there is indeed a field dependence to the rho xx. So, there are so many such problems. Then there is the conductivity, for example. Drude model gave us a conductivity formula n squared tau by m for DC conductivity, and of course, also gave AC conductivity formula, but those formulas were not fitting the experiment. There are temperature dependencies, there are frequency dependencies, that means energy dependencies, which were not coming out to be correct. So, the obvious solution when quantum mechanics came in around 1925 was that use quantum mechanics to describe these systems, this collection of electrons, and it was since of course, electrons are fermions, spin half fermions, and one immediately realized that a classical approximation will not do. Then Sommerfeld of course, was the first to pick up the the Q and did a calculation for the specific heat, which we will show at a later class, and came out with at least the temperature dependence, linear temperature dependence correctly, though the coefficient was still not agreeing with many experimental facts. Now, to do a quantum mechanical theory of a large number of electrons, one has to make again some assumptions, and the obvious assumptions people did in the beginning was that these electrons are independent again. They are just like the gas of electrons that we were doing, but with a quantum mechanics, that means Pauli principle built into it. So, and then what you have to do is to solve the Schrodinger equation instead of any classical equation, Newton's law, for example. So, instead of instead of taking a collection of electrons which are interacting with each other, interacting with the lattice, one still works with the assumption that these electrons are free, they are independent, but they obey quantum mechanics. That is the first approximation that we are going to do now. Okay. So, the equation that one now the electrons are now supposed to follow is basically Schrodinger equation. This is the del square operator psi equal to E psi. So, then we of course, we know that this can be written as just the del square of psi equal to E psi. The solution to this will be the one that we are after in a solid, but this solution is quite straightforward because there is no potential here. So, the energy is constant. So, we know the solution will be like a either depends on the boundary condition, either it will be a standing wave or will be a travelling wave. One can choose the solution depending on the boundary condition. The obvious boundary conditions that one can think of are basically two. One is this that suppose this is my solid and these are the two boundaries, and the electron is confined within this boundary. It is 0 outside, and it is whatever it is, the solution of Schrodinger equation inside. Now, this we know gives us a standing wave kind of solution, and that solution is standard solution, which is so let me write down this boundary condition. So, this boundary condition is psi at x. So, this is suppose the length of the system. It is extended in 3 direction. It is a cube. So, x plus L y z equal to psi of x, y and z, and both are equal to 0 because x equal to 0 at x equal to 0, y, z. So, at the two boundaries the wave function vanishes. It is like putting an infinite potential at the boundary. Now, if this is the solution, then of course, the wave function is psi x equal to some constant which has to be determined from the normalization sin n pi x by L. Similar conditions in the y and z direction gives sin n. So, let me write it n x n y pi y by L into sin n z pi z by L, where n x n y and so this number n. So, I put an n here, this number n is n x, n y, n z, these are positive integers other than 0. Now, this solution is a standing wave solution. It had to be because the wave function has to vanish here and it just bounces back and forth. So, it forms a standing wave, but this is not very useful for calculating, for example, transport, where you have to carry charges from one side to the other, carry energy for example, and so one chooses a different boundary condition which is more handy and more useful. So, let me just do that. That is called the periodic boundary condition. It is also called Born von Karman boundary condition PBC or Born von Karman boundary condition. Now, this boundary condition is let me write down again in terms of psi of x plus L, then I will explain what it means. Y z is equal to psi of x, y and z. So, what does it mean? Let us just look at in one dimension. So, at any value, so at 0 for example, x equal to 0, this equates 0 to L. So, the electron, as if the electron moves from here, suppose it moves from x equal to 0 to L, it leaves L and then reappears through x equal to 0. So, that means there is no boundary anymore, right. The effect of boundary is gone in this way of looking at things, even under these boundary condition. Not that the boundaries are not important, they have become important in the last 15 years or so. Nevertheless, this is the one that we will use, and so this boundary condition basically connects the two sides. So, that means a line now becomes a circle. So, whatever was 0 is also the L. So, the electron moves in a circle, and I can have a travelling wave solution. Similarly, for y and z direction. So, a 2 dimension, for example, I can still imagine the geometry, the topology of this boundary condition. So, what I will do is that I will equate this boundary with this boundary and that boundary with that boundary. So, it is like a torus, but in 3 dimension, of course, the topology is too complicated and we cannot sort of imagine it, but assume that that is the boundary condition. So, in that situation, the wave functions can be chosen as just like we did in 1 dimensional quantum mechanics. We can choose a wave function psi of r, vector r is equal to 1 by root v e to the power I k dot r. Okay. Now, the value of the k is kx, ky, kz. So, from here I can easily find out certain quantities, because I know the operator, for example, for momentum. Momentum operator is minus I h cross grad. So, if that operates on this psi, let me put a k index here, because it also depends on k. K is something we will determine from the boundary condition. It has the dimension of momentum, of course. So, I h cross grad psi of psi k r will give you p as h cross k. So, p will become h cross k. Okay. And energy is basically that from the Schrodinger equation itself, you can get operating by del square operator is becoming h cross, or you can also use h cross p square by twice m, h cross square k square by twice m. So, this is still a free particle, its a momentum is h cross times k, and its this thing so k dimension is inverse of wavelength, and this inverse of length basically. So, k is 1 by lambda, usually we write 2 pi by lambda. Now, p is h cross times k, and E is equal to h cross square k square by twice m. Okay. So, this is what these are things we will be using. Okay. So, the other thing that I wanted to mention was that the way I have chosen this wave function is such that d3 r mod psi k square over a volume V is equal to 1. So, that is the normalization 1 by root V that I chose, so that this integral becomes 1. Okay. So, the electron is somewhere in the volume V, where we do not know. It is a plane wave solution, because you can see that so it is a h cross e to the power I k dot r. Now, I have to determine the as I said, the value of k from the allowed values of k from the boundary condition. Now, why did I say allowed values of k? Because we already knew from one dimensional examples that not all k values are allowed. So, let us see which k values do we get from the boundary condition, say x plus L y z equal to e to the power I k k x x plus L plus k y y plus k z z equal to e to the power I k x x plus I k y y plus I k z z. That means, e to the power I k x L is equal to 1, okay, which means simply that k dot L k x into L equal to 2 n x into pi, where n x can now be 0, plus minus 1, plus minus 2, and so on, integers. So, similarly k y and k z will give me the same relation. So, the boundary condition now tells me that there are these each k value is restricted. So, between k n x equal to 1 and n x equal to 2. So, there is a distance of 2 pi by L. For each 2 pi by L distance, I will get one k value. So, in one dimension, and in 2 and 3 dimension, it will become area 2 pi by L into 2 pi by L and then 2 pi by L cube. So, this actually very is important because I will start counting the number of states in the K space. So, that is something that is an extremely important quantity, is often called density of states, and that counting is useful in calculating integrals involving physical properties of solids or electrons in solids. Okay. So, my 2 pi by L is, so let me just show you in a view graph how does it look like. So, let me go back to sorry, yeah, here for example, this is the state counting. So, we are counting the state. So, what did this previous page tell us? It told us that there are these points in the k x. For example, this is a 2 dimensional case. So, in each 2 pi by L distance there is one point, and these are allowed values of k. Not all, any k value in between these two is not allowed. Similarly, along the y direction, k y direction, between 2 there are no k values allowed. So, that means this shaded area, which is area is 2 pi by L square, contains only one allowed k values. So, that means in 2 dimension, for one k value I need an area of 2 pi by L square. Similarly, in 3 dimension, for one k value I will need a volume of 2 pi by L whole cube. So, 8 pi cube by L cube. Now, L cube is the volume. So, let us just go back to what we were doing. Okay. So, what I will do now is that as I just showed that 2 pi by L, so a volume in K space two pi by L cube contains 2 pi by L whole cube contains one allowed k value. That means one state, that is one state. Okay. So, that means for each state I need this value. So, that means this value contains one state. So, suppose I have omega k volume in K space, how many states will that contain? Will simply this divided by 2 pi by L cube, which is V times omega k times 8 pi cube. So, that is that gives me the number of states, allowed states in a volume omega k in the k space. Remember, this V is the real space volume. Now, the interesting thing is that how do I now put the electrons in these allowed states. So, since E equal to h cross square k square by twice m, two things are interesting. One has to be noted, two things have to be noted. One is that the h cross square by twice m into k x square plus k y square plus k z square. So, the constant energy surfaces are a sphere in the on the surface of a sphere in the momentum space. Since it just depends quadratically on k, it is like take any sphere of radius k, on the surface of that sphere the energy value does not change, although kx, ky, kz will change. So, for all k's on that surface the energy remains the same. The other thing is that the lowest energy state, is for k equal to 0, which is the 0 energy state at 0 temperature. So, we are looking at the ground state at 0 temperature, and this is the first state that we have to fill in, because that is the lowest energy state. And we know, for example, this in one dimension for this allowed this k square spectrum is like this. It is a parabola. E versus k, kx for example, in suppose I am working in one dimension, then my allowed k values are here, suppose these are my allowed k values. So, how do I fill in these states? All I do is that I put electrons in each of the k space starting from the lowest allowed state. So, if k equal to 0 is allowed, then I will put k equal to 0 k and k equal to 0 state. So, in this way 0 energy state is the k equal to 0 state. So, so I go ahead and just fill in this is called the filling of the states. So, I basically fill up all these states from the lowest energy. Now, the interesting thing is that again in 3 dimension, for example, that every k you fill up, all the k's you fill up, k's which correspond to a same k square will give me the same energy. Okay. So, that is something we have to remember. Now, if we go on filling, there are very large number of states, like I mean there are 10 to the power 23 order particles. So, that many atoms. So, each atom contributing at least one state will give me a very large number of state. The other way to put it is 2 pi by L cube. L cube is the volume. So, that volume is very large compared to the dimensions we are discussing of the wavelengths of electrons and so on. So, the number of states that we are having here is exceedingly large, and then they are extremely densely packed, in the sense that the difference between k states is very small, and in such case, in such situation, it will look very symmetric. There is no anisotropy in any direction. The energy goes as k square. So, the way I fill up the energy surface is basically the momentum states is like a sphere. So, if I fill up all the states that I needed to fill to occupy my n electrons, then the final surface, the highest energy surface in the momentum space will be a sphere, obviously, right. So, that surface, the spherical surface, suppose its energy is EF, EF is called the Fermi, this energy is called the Fermi energy, and that surface that separates the unoccupied states from the occupied states in the momentum space is called the Fermi surface. In this case, it is a spherical surface of a sphere. Now, if so, I can write down the EF in terms of h cross square kf square by 2m. So, the argument is now, I suppose it is clear that I have very large number of states, and the separation between states is 2 pi by L, which is exceedingly small compared to the volumes we are talking about, and then so many states have to be filled up, and so then it will look like a and then the spectrum is a quadratic spectrum. So, the way you fill it in will finally look like the occupied part of the momentum space, allowed states in the momentum space will look like a sphere. Okay. And the highest energy, which is the last occupied states on the sphere, is called the Fermi energy, and the surface in the momentum space of that sphere is basically it is separating the occupied from the unoccupied states, and it is called the Fermi surface. Now, these two things, Fermi energy and Fermi surface, have a lot of bearing on almost every calculation you do with electronic properties of solids, and we will use some of these things now. So, first thing I have to do is to count the number of states, because they are very densely packed. I can define a density of states. How many states are there between a volume, between two spheres of volume k of radius k and k plus dk, for example. That gives me the number of allowed momentums in an annulus which is whose width is just dk. Similarly, I can also calculate the number of states between two energies, which is E and E plus dE, and these number of states are very large, they are very dense. So, it makes sense to talk about a density of states rather than sum over every state. Suppose you want to do an integral or a sum, you may go over every k value, but then the k values are 10 to the power 22, 23 order. So, instead you convert it into an integral, and then you require to know what is the density in a region of in a volume of k space, or in a region of energy interval between E and E plus D. So, that is what we are after now.